The Pathway Tools Omics Dashboard is a new tool for visualizing omics data, such as gene expression data or metabolomics data. In Part 1, we introduced you to the overall organization and operation of the dashboard, showed you how to upload omics data to the dashboard, and demonstrated the various features that allow you to extract insight from your datasets. In this second webinar, we examined several advanced features, including the handling of datasets with multiple replicates, use of significance values for enrichment analysis, and dashboard customization options. We will also see an example using a metabolomics dataset. This spreadsheet contains normalized RNA-seq time series data for the anaerobic to aerobic transition in E. coli. The data are organized such that 3 replicates are available at each of the 6 time points. When we save this data as a tab-delimited file and upload it to the dashboard, we see data from all 18 data columns. However, what we would really prefer to see is a simplified view in which for each time point the values of the 3 replicates are averaged together. This is possible using the series grouping option. We start by specifying how many groups we want to create. Since this experiment has 6 time points, we specify 6 groups. Note that for performance reasons, the maximum number of groups supported is 10. Now we just need to specify which data columns belong to which group. In this case, the first 3 data columns contain replicate data for the first time point, so we group them together in group 1. The next 3 data columns are grouped together in group 2, and so forth. In this example, all data columns are assigned to groups, and each group contains the same number of data columns, but this need not necessarily be the case. The groups are given default names of G1 through 6, but you should feel free to assign your own names. When you have finished filling out the form, click Update Display. We now see a simplified display that contains only 6 time points. Each small dot in the plot is now the average of the 3 values for that gene. If we open the Series Selection panel, we are now selecting which groups to show rather than which individual values. Note that dashboard responsiveness is likely to be a fair bit slower in this mode than if you had just uploaded pre-averaged data values. If you are finding performance to be a problem, you are probably better off averaging the replicate data in your spreadsheet and only uploading the average values. However, an advantage of this mode can be seen when we drill down to gene level display. In addition to the average values, we can now see the value for each individual replicate. This gives us some idea of the variation among replicates compared to the variation between time points, and gives us a visual indication as to how significant any changes might be. Speaking of significance, I'm going to shift gears now and move to a different dataset. Unlike the previous examples, which have all been of gene expression data, this is a metabolomics time series dataset showing the change in abundance of various metabolites in a Helicobacter pylori cell in response to the introduction of metronidazole. The first column contains metabolite names. This table has actually undergone a fair amount of statistical analysis already, as it combines results from multiple replicates. These last 5 columns contain the average fold changes relative to time 0 for each metabolite at each time point. Replicate analysis has also generated a p-value for each metabolite at each time point, indicating how significant any changes might be. Traditionally, such p-values have been used to dismiss results deemed not statistically significant, or to identify candidates with significant changes in order to conduct an enrichment or other analysis. The dashboard will not omit any results unless the user chooses to exclude them from the uploaded file, but it can use the p-values to show the result of an enrichment analysis. When I upload this dataset, you can see that I've specified that the items in the first column are compounds, and I'm uploading all the data columns, both the ones containing the fold changes and the ones containing the p-values. The other parameters all refer to the fold change columns. The dashboard is now showing me both the p-values and the fold change values on the same scale, which I don't want, so let me first turn off the display of p-values. Before we move on, let me point out some differences in the dashboard when displaying metabolomics data instead of gene expression data. You will notice that the panels of non-metabolic functions are no longer present. Each of these small dots now represents the value for a single metabolite in one of the pathways in this class, and the large dot is the average value over all metabolites in all the pathways of this class for which data was present in the dataset. When I drill down to the lowest level, the values along the x-axis are now metabolites, not genes. This is likely not the complete set of metabolites in the arginine degradation pathway, just those for which we have data. We can show the pathway and operon diagrams as before, but we obviously do not have any data for transcription factors in this dataset, so the regulators option is no longer available. Now let us use the p-values we uploaded to perform an enrichment analysis. Enrichment analysis captures the degree to which a statistically significant number of genes or metabolites within any given subsystem are undergoing significant change. For each fold change column, we specify which column contains the p-values for that column. We then specify a significance threshold. Let's say 0.01, which means that all metabolites that have a p-value less than 0.01 for a time point are considered significant. Note that the significance columns need not be p-values. They could be any measure of significance. For example, if we just had data for a single replicate and wanted to consider significant any gene or metabolite with more than a 2-fold increase, we would specify each column as its own significance column, and then specify that significant values are those greater than or equal to 2. We can specify an optional statistical correction function here but I'm not going to at this time. The dashboard uses the significance values and the threshold to determine the set of significant metabolites for each time point. It then computes enrichment p-values, which are not related to the p-values in the supplied dataset, for each cellular subsystem using a Fisher-exact hypergeometric test, applying the selected correction, if any. We convert the p-value for each subsystem to an enrichment score by taking its negative log base 10 and plot them all on the dashboard. The height of each bar now represents the enrichment score for the subsystem at that time point. The actual enrichment score is printed near the top of the bar, although if many are close together, they may overlap and be hard to read. Let me increase the panel scale to see them better. In some cases, you can see an additional line extending from the top of the bar. Let's look at this first time point for amino acid biosynthesis. This line indicates that there are one or more subsystems under amino acid biosynthesis that have a higher enrichment score than amino acid biosynthesis as a whole. The height of the line is the highest enrichment score for any child subsystem. The presence of this line suggests that it may be worthwhile to drill down for more information. We can see that the enrichment score for the first time point was almost entirely due to changes in the cysteine and lysine biosynthesis pathways. Because the enrichment scores are for subsystems, not for individual genes or metabolites, if we drill all the way down to the metabolite level, we revert to showing the fold changes for the individual metabolites. While the changes in the early time points may be small, they are significant. And we can see that as the experiment progresses, that O-acetylserine in particular is undergoing major changes. We can return to the enrichment panel and click Disable Enrichment Mode to return to the original display. Shifting gears yet again, I'm going to switch back to the gene expression experiment we saw at the beginning of the previous webinar and show you how you can customize the contents of the dashboard for your own needs. For any panel, there are two different customization commands in the options menu. You can customize the existing contents of the panel, or you can add a new subsystem to the panel. Let's look at the different ways we can update the energy metabolism panel by selecting Customize Panel. Each subsystem has a unique identifier, which you cannot edit, a full name, which appears here as the panel label and also in tooltips, and a short name, which is used as the x-axis label when the subsystem is a component of another panel. The energy system is not a subsystem of any other panel, so it does not require a short name, but we can see that each of the panel components have both a full name and a short name. From this dialog, we can edit any of the names, we can remove one or more components from the panel by clicking the X, and we can use the arrows to reorder components. Note that for most gene-level panels, the genes that make up the panel are computed from the pathway genome database and cannot be edited. Any changes we make here will be sent back to the server and will persist for the rest of our current session, including for any other datasets we view in the session, unless we remove them. We can specify whether such changes apply to datasets from any organism or from the current organism only. As we will see later, you can also download your set of customizations to a file on your computer, so you can upload them again into a future session. Once you are satisfied with your changes, click Apply Changes. This will cause a full page reload, and then we can see our changes reflected in the resulting display. To add a subsystem to a panel, use the command Add New Custom Component. There are 4 different options for the new subsystem. You can add a pathway or pathway class, a Go term, a custom list of genes, or a composite panel that contains a set of pathways or Go terms. Let's first try adding a pathway. Start typing a pathway name, you can then use the autocomplete functionality to add the desired pathway or pathway class. Defaults for the name and short name will be provided, but you can edit them. Click Add Component or Panel to complete the operation. The exact same procedure should be followed to add a new Go term component. Let us now repeat the procedure, but this time add a subsystem consisting of a custom list of genes. We need to provide a unique key here, as well as the names. We then type or paste in a list of gene names or identifiers separated by white space. There is no autocomplete functionality here. When we have finished creating our list, click Search. Note that I have intentionally included a couple of names that are not recognizable genes. The gene names that were matched to valid genes in EcoPsych are replaced by their identifiers. If there were any names that could not be found, they are listed here. This gives me an opportunity to edit them and try again if I wish. Once I'm satisfied with my list, I can create the subsystem. The energy metabolism panel now contains my custom component, and I can drill down to see the expression data for those genes, like for any other plot. Adding a new composite panel works the same way as adding a custom set of genes, except that instead of gene identifiers, you should enter identifiers for pathways, pathway classes, or Go terms. If I want to create this new panel as a top-level panel instead of a component of an existing panel, I can open Customize Contents and select Add New Top-Level Panel. This command brings up the same dialog with all the same options as before. There is currently no way to reorder the top-level panels, but that may be added in a future version. Now that I have added several customizations, a number of other options have appeared in this control panel. The View or Manage Customizations option shows me all my current customizations. I can click the X to selectively remove any that I no longer want to click, that I no want. Other options here are to show the default display as it would appear without any customizations, without actually deleting the customizations, or to delete all my customizations. I can download all my customizations to a file on my computer, or I can upload a previously saved customization file. This covers most of the dashboard functionality. Before I go, I want to show one final option. If I was logged into my Biopsych account when I originally invoked the dashboard, I can save the dashboard dataset to a smart table. Along with the data, this also saves a number of my settings, such as the default enrichment and display preferences, any groups that I've defined, and my significance columns for enrichment analysis, though not my content customizations, so that if I ever want to upload this smart table back to the dashboard, those preferences will be restored. To re-upload the dataset, you can go back to the entry page and select Import Data from a Smart Table. Or, if I go back to my original Dashboard tab, I can see that it has provided me with a URL that I can paste into a new browser window to regenerate the dashboard display automatically. If I make my smart table public or shared with selected other users, then I can share this URL with them too. Note that this operation assumes that the contents of the smart table have not changed since it was saved. It is okay to edit the title, description, and column labels in the smart table, but if you add, remove, or otherwise change columns, results may be unpredictable. This concludes the Omics Dashboard webinar.